Please welcome President Dr. Katrina A. Armstrong.
So grateful to be here with all of you, and I'm delighted to welcome you to the last session of Columbia's AI Summit. I want to acknowledge Shifu Chang, Garud Iyengar, and Jeanette Wing for their expertise, vision, and leadership, and also thank everybody, all the Columbia scholars and researchers who have participated in this extraordinary event. I also want to really welcome our distinguished guest, Professor Haddadin, who's come from Munich to deliver the keynote address. Finally, I just want to thank everybody who's worked so hard to put this together, students, faculty, staff. I know it takes a village, and I'm incredibly grateful. I think, of course, as we know, we've come to discuss artificial intelligence, but I will say that for me, we've also really recognized the power, I think, of university or Columbia intelligence. So as I travel around this campus and I write, I think so often to all of you, so much of what matters to us is our mission as a university. I don't think I have to share with anybody here that we are in the epicenter of what can feel like a seismic shift in how the world sees our universities and our approach to higher education. It can feel sometimes like so many things are happening at once, all of them of existential importance. But I think for all of us, even as we rely on AI to bring data together, to help us understand a new way of seeing the world, I think for all of us, as we navigate these times, we also have to stay grounded in who we are as people. For me, that means staying grounded in being a physician and a teacher, being able to look at the things in front of us and understand honestly what we can do better, focus on how we can fix things and move forward, make decisions that are essential for our progress, but never, ever take our eye off of what we mean to society, to our students, to our patients, and to all of those who benefit from the remarkable work that goes on here. I know that this requires courage of all of us at this moment, and I hope that this day, these experiences have helped you see the incredible opportunity, the incredible privilege that we have to be here and be part of this work. I cannot imagine a better example of Columbia's unique ability to contribute to society than these sessions and these discussions today. I know that critically important questions are likely to come of this. How should we think about guardrails for public consumption of artistic production and news content generated by AI? How do we generate a coherent framework for investments in the computing power that's needed for us to really unleash AI's full promise without exacerbating the climate change we see around us? What will this mean for our labor markets, for our students here today, and what they will do to lead fulfilling and meaningful lives? How can we ensure that we remain focused on safety and ethics? But as I stand here and think about the importance of those questions, it is also deeply reassuring me to know that there is no institution better poised to work on those questions, to move us forward, to provide light amidst darkness than this great, great university. We have people from nanotechnologists, just explaining robotics and surgeons, to leaders in architecture and urban planning, policy making, international affairs, social work, legal scholars. There is no other university like this. And so I am so grateful to be able to be part of this, both for the individuals who are coming together, but particularly for the collective good that we can all do as we take on these challenges. I'm excited to join you in this journey, and thank you again for being here. Thank you very much.
Thank you, President Armstrong. Good afternoon, good evening, everyone. I'm Shifu Chen, Dean of Columbia Engineering School. It's really my privilege, my honor here to introduce our keynote speaker at this first AI Summit at Columbia University on this beautiful campus. This event has been the combination of our collective effort to bring together all the amazing activity in the area of AI across the whole university. And you have seen many exciting sessions today on 3 campuses here today. As you know, Columbia AI Initiative is centered around this unique approach called AI plus X. It highlights our cross-disciplinary breadth and depth in so many different fields: engineering, science, humanity, medicine, business, public health, law, policy, architecture, journalism, arts, you name it. Every discipline you can find on campus in academia. Our goal is to leverage our collective strength to advance our core mission of the university: research, education, and innovation. I hope today you have been able to enjoy many exciting sessions in all this wonderful dimension: research, education, and innovation in the space of AI. Today, I'm very lucky to have one of the world's leading pioneers and really thought leader in robotics and embodied AI with us. And I'm sure our speaker will explain what embodied AI is and why it's so important. Sammy has been conducting groundbreaking research in this area of embodied AI, which many of us are called the next frontier of AI. This area of embodied AI is an area focused on building intelligent systems that interact with physical environments, no matter what scale you name it: molecular level, atomic level, atmosphere level, and underwater, in the space, everywhere, physical environment. And this system that are engaging, learning, and adapting. Sammy envisioned that an embodied AI system can work along humans, not to replace human. It's to help human to expand and extend our ability, particularly our ability to solve the real world problems. He holds a degree in electrical engineering, computer science, and technology management from TUM, Technical University of Munich in Germany. He received his doctoral degree from RWTH Aachen University, joined Gottfried Wilhelm Leibniz University of Hanover, and then become professor and director of the Center of Digital Technology and Management in TUM. He has founded several startup companies and very well known, and co-founded a German robotic company called Franka Amica GmbH. I'm not sure that's the right pronunciation. It's so well known. His invention of the Panda robotic arm was named one of the Time magazine 50 best invention in 2018 and was featured in National Geographic. His patent for the tactile robot is part of the milestone made in Germany connection in German Patent and Trademark Office. Sammy has also served in many important initiatives and also on expert panel around AI. In 2020, he was appointed chairman of the Bavarian AI Council. For his work, he has received many distinguished awards, including Gottfried Wilhelm Leibniz Prize, and with his colleagues, the German Future Prize. He was elected to German National Academy of Science, Leopoldina, in 2021. Without further ado, please join me in welcoming Sammy Haddadin.
Thank you so much, Dean Chang, for the kind introduction, and President Katrina Armstrong for doing such an amazing job here at Columbia for interdisciplinary AI research. So not only technology, but really AI that kind of does the right thing for society. I think that's very inspiring to think about the use of AI. And I'll try in my keynote address to talk about not only robots and the search for universal intelligence, but what embodied AI means and how can we really benefit from it, but also why is this such a challenging endeavor that lies ahead of us. So I think it is safe to say that one of the most pivotal events in 2016 took place where Lee Sedol was beaten by Google DeepMind's AI engine in Go, similarly to almost 20 years before, not quite, Garry Kasparov, my childhood star, and in chess against Deep Blue from IBM. So we see that many of the AI advances over the last years have really marked superhuman performance, as we hear a lot. But I think what is also really clear is that the year 2023, especially January, marked kind of a pivotal moment because ChatGPT opened up to the public and we could actually use generative AI for the first time widespread in society. It was quite amazing what people have been using it for, but in particular what kickstarted this January event in 2023. At the same time, it's also well known that AI has really become widely adopted as a new scientific discipline. So with 2024 Physics Nobel Prize being awarded to Geoff Hinton and John Hopfield for groundbreaking contributions to artificial intelligence, in particular neural networks. At the same time, I think it's very clear that we still have a long way to go. So if you think of AI to be basically centered around the two lines of self-awareness and embodiment, then it is pretty clear that the things we see nowadays are still largely happening in the either digital space or using offline physical data, for example, for the AlphaFold mechanism or other foundation models that are used for prediction in various applications. However, if you really want to become or to build AI systems of very high self-awareness and acting in the physical world, then the holy grail of a complete embodied AI system, we recently heard Jensen Huang saying physical AI, I think basically being the same thing. So an AI system that has a physical body that is interacting with the physical world and is able to learn, adapt, and interact with this world, including the humans living within it. Oh, thank you so much. It was a long flight. So, what does embodiment mean? Similar to the human, here the famous homunculus depiction, we as roboticists build not only the systems, the morphology of the technology, but in particular we also build the brain, the central nervous system, so the control system that is able to give the embodiment the right ability to interact and act in the physical world. So this kind of co-evolution of the intelligence and embodiment is what makes these systems so complex, because they actually ask the question, how can synthetic systems interact in the physical world in a world that is hardly predictable and in particular is largely unknown to the physical agent we call a robot. So in today's talk, I'm going to talk about two major points. The second one being much smaller, but I think giving a little bit of an outlook of where embodied AI can take us in the larger scale of the discovery, autonomous knowledge discovery. But first of all, I want to talk about the building of the embodied AI system, so the robot itself. For a roboticist, embodied AI and robotics are very similar to each other, so we have a hard time of making a clear distinction. Therefore, bear with me of using robots and embodied AI almost as interchangeable words, because for the fundamental approaches, there is very little difference, in fact. So we have seen a dramatic increase in robot deployment over the last years. It's clearly exponential, especially the last 2 years. We have seen even humanoid companies coming out of nowhere. So we see humanoid robots now all over the place. So there's exponential growth in the embodiments, but I will argue that there is still a lot of things to do before these embodiments really become truly smart and truly intelligent to physically interact in our physical world. But what does an embodied AI system need? First of all, it needs to understand it has a body. So this robot you see is basically born without a program. It just has its sensor. It has the ability to move. And what you see here is a robot that from scratch is able to experience its own sensory perception without knowing where along its body these sensors are located, but it builds its own mental map of its kind of spatial dimension, so what we call the self, essentially. So a kinematic map of its own limbs, of the motions, and this purely based on machine learning running on the real-time data that you see in the system being used to then build a very accurate map with closed eyes, so based on internal perception alone. So basically you closing your eyes, moving around and understanding the spatial dimension that you have and the movement that you can execute with that. So this kind of understanding of the embodiment itself then interacting with the physical world is the fundamental first step in building a truly embodied AI. Obviously, we want to build systems and embodied AI systems that are able to, regardless of the topology, regardless of the morphology even, to build their own mental map of their existence. So a system that from scratch is able to essentially, bootstrapping the problem of creating the self, independent of the morphology, whether it's a humanoid, a crawler, or any other morphology of robotic existence. So this obviously is a very fundamental question to answer, and has been quite a problem for many years. At the same time, robotics goes back quite some time, but I think it is safe to say that many of the things I'm going to talk about today are not really kind of related to these kind of robots. So this is actually the first industrial robot that was entering physical reality or industrial reality in the 1950s, the Unimate system. As all of you can see, this is a robot that is very heavy, very dangerous, and obviously none of us wants to interact with that system. So I think it's clear that this would not be the Rosie or the Johnny that we would like to see in our kitchen environment. Probably lots of things would basically break, especially humans around operating them. So we want to obviously have different systems to really realize that kind of future. So where physical interaction between the human and the robot are as safe and intuitive as they can get. Obviously, not only with the elderly, with us, but in particular with children. So the robots have to be extremely safe to really be operating around us. We know that obviously in the physical space, there's very different dangers from the purely digital domain, especially the physical harm that can happen due to the interaction of physical machines with the human body. So this basic interaction problem has been researched for almost 45 years. In particular, Osama Khatib, Gerd Hirzinger, Siciliano, and others in the US, in Europe, but also in Japan have been laying the foundations in the early 80s. So of robots that can actually, in principle, physically interact with the world. So the basis were there in the 80s actually. However, only recently we were able to build robots that are truly able to do similar motor skill tasks that seem to you and me very trivial, but actually robots that are able to operate, for example, a key and insert it blindly with a sense of touch and compliance into a hole. Things that you and me can do with 3 or 4 years, 5 years maybe, but robots were not able to do them autonomously only until recently. So, coming back to the question of what a robot really can do, kind of asks also the question, can we connect basically what robots can do and can we categorize that? And how do we fundamentally understand that robots have certain innate abilities, and how can we classify, understand, and make sure that for the vast skills that these robots are supposed to do in the physical real world, they have to connect basically the innate ability, not only the self, with the possibility so that with the possibility of the application that these robots can execute. So we basically asked the question of an embodiment system, how can we categorize these robots and their morphology and capability in a sense that we can then automatically reason about them and understand, given that I can see a robot, what can that robot truly do? So we took some inspiration from Charles Darwin's Tree of Life to connect basically the capability of a robot with its morphology to then fundamentally classify, similar to the Darwin, birds, that kind of connect the capability of the system and their morphology, meaning that the body has a certain functionality timed and tied together with its intelligence, so the algorithms of learning and adaptation, to then fundamentally do a classification that gives you the answer to what can that system really do and what can it learn and what can it execute. So coming from the perspective of the machine, we introduced recently the tree of robots that basically gives a fundamental classification attempt to understand not only the morphology of the system, ranging from its scale to the technology behind it, to the kind of morphological topology of the system that is ranging from drones to humanoids to manipulators, but in particular measure fundamentally their capability, which is important to then really run data-driven algorithms on these systems. So we, for example, introduced the first time a fundamental fitness classification, similar to what we know from the evolutionary theory, that actually automatically now classifies what the abilities behind robots are. So typically we see a robot, we think we know what they can do, but fundamentally their capability is not yet measurable. So this kind of fundamental understanding of their innate ability has now been understood and can actually build the fundamental for this tree of robot that then can serve kind of the encyclopedia of skills of arbitrary morphologies and robots. And if these robots can do all these things that we are promising, so they can interact with us, they can help us at home, they can help us at work, in helping us to stay at home also for elderly people, then obviously we also need to ensure that these systems are fundamentally safe. I mentioned that already. And someone who foresaw that very early on was Isaac Asimov, who in 1954 was proposing his famous 3 laws of robots. And the first one was a robot may not injure a human being or through inaction allow a human being to come to harm. And what is the reality that we see today? Is this actually already there, or what? Where are we and what do we have to do? Just recently we have seen a humanoid robot almost giving a headbutt to a person in an incident in China. And obviously these kind of situations are very, very dangerous. So this system is very fast, very dangerous. It could have caused a lot of harm. So we were lucky in some form that nothing happened there. So this reminded me to my own PhD thesis that asked the question, can we actually build safe robots and how can we approach Asimov's first law? And as a true scientist, we like to do self-experiments. So this was the first robot that was actually able to become, and I sometimes do the joke that this was actually my evil twin brother, and obviously, yeah, he's not with us anymore. But in reality, this kind of laid the foundation for physical interaction in the real world. So actually now we see an entire field we call human-robot collaboration, cobots, tactile robots. So robots that can physically interact with humans have become reality because of these basic experiments, because we showed that you can build lightweight robots that are intrinsically safe for the interaction with humans. And in fact, these robots are so safe that they can detect and react to collisions and contacts with the environment blindly at milliseconds. So 1,000 times a second, these systems can monitor the interaction with the world. And here you can see how the system is so gentle that even with a nail at the end effector, the robot is able to stop without destroying the balloon in this example. A few years before, I again laid the foundation for these kind of reflex sensors, so the sense of touch of robots, again in another self-experiment. So I wanted to obviously build robots that are able to help us in the kitchen, and we wanted to see whether our collision handling systems are so safe that nothing can happen in these experiments. So you can see, in a way, my thesis was a bit different. Still, next question is obviously, now that we have robots that in particular are safe and interactive, but can we actually make them do things such as this is actually my daughter when she was about 4. I always do these experiments with my kids, so they tend to be part of my science. And back then, I wanted to understand, can I make robots actually learn to interact with the world by solving the key into whole problem? She was making a big mess in our living room, so I took the opportunity and said, her name is Franka, by the way, so she's the name that gave the name to the company. And back then I kind of asked her, so Franka, if you do such a mess in our living room, let's do an experiment with you. So here's a key, go to the door and see whether you can open it in less than 10 trials. If you succeed, then you don't have to clean up. She ran as quick as you could. I mean, you can imagine. She ran to the door, and in particular, I was kind of wondering whether is it too simple to do it in 1 trial, or does it take forever? She did it in 7 trials. So obviously not a big data problem. So somehow in her body there was this innate intelligence that made her able to insert the key into the hole in 7 trials, so very few trials, until she was actually able to do it. So, and if you fast forward to today, if we now use just purely digital AI, so standard reinforcement learning, standard deep reinforcement learning, which you see on the right side, and kind of compare it with embodied AI systems that are able to understand basically the physical environment and what does it require for a robot to actually insert an object into another object and mate them. And in particular, under the understanding that the robot is able to kind of understand, whatever that means in a technical sense, that it is embodied, so the interaction is more than just a purely digital event, then we can see that there's a dramatic increase in performance. In fact, it's orders of magnitude. On the left side, you see how in very few trials, so similar to my little daughter, after a few trials, this robot is nowadays able, within 5, 6 trials, sometimes 1 minute, 2 minutes, able to converge even optimally and insert the key into the hole. On the right side, you see a pure brute force attack. End-to-end deep reinforcement learning actually takes sometimes weeks until we find solutions for the first time. So this really I think underlines the notion that physical existence, embodiment are really important to be built into the AI system so that we can really make them perform in a manner that really achieves human-level performance, not only in cognitive tasks, in chess playing and Go, but in fact in physical tasks that seem trivial to you and me, but they are not trivial for robots in embodied AI systems. So, and in what we call tactile manipulation, there are so many things that have not been yet addressed. So we need to kind of bootstrap that whole problem because it's infinitely many problems we still need to solve. Only very few things have been automated by robotic systems. And how can we really do that? What we have been introducing recently is kind of a structural machine learning approach that tries to essentially understand what tactile interaction really is, coming from the question of taxonomic understanding. In order to manipulate something, you need to essentially understand what kind of interaction happens between the embodied AI system and the physical object it's manipulating, which is basically a power interaction. So a physical system interacts with another physical interaction, with another physical partner, exchanging energy, therefore power. So you need to understand what kind of twists and wrenches, so motion and forces are interacted. And if you do a kind of structured analysis of that problem, you can actually come up with a machine learning pipeline that fundamentally seems to be much, much better suited to tackle that embodied AI tactile manipulation problem, so the interaction with the world. So if you express that physics matter in the machine learning problem itself, it seems that fundamentally that structure increases the speed of the learning process dramatically compared to a pure uninformed end-to-end approach. So, and what you can then do is, in fact, not only in the lab interesting things, but you can solve industrial tasks. So this kind of AI is, as of today, running in real factory floors in the world. So you can now automate, for example, recycling tasks that at the moment are really a big problem in e-waste management. We cannot recycle all the electronics waste that we are producing. Now we have been building the first robots that are actually able to disassemble electronic waste, segregate the different parts into the right bins, and then feed them into the recycling system. You can even now do autonomous manufacturing of machines themselves. So you see on the left side a very complex and for the layman very unintuitive manufacturing object that is being assembled. On the right side you see, on the left side it's the manual assembly, on the right side you see how the embodied AI system is now learning autonomously how to manufacture this very strangely looking metal piece. And just within a few trials, I think it's about 20 trials, the robot is able to insert and mate and assemble really this very complex assembly process, something that couldn't be done until recently. And with this kind of embodied AI system that are able to reach now industrial performance, we can actually now build autonomously machines. So this was actually a gripper for production of these kind of beverage machines. So very complex machinery can now be automatically manufactured by robots at a scalable and high productivity kind of scale. So, but how does that scale fundamentally to different tasks? Do we now have to reteach? Do we have to retrain every new skill? That would be infinitely many. It sounds very unlikely that this is possible. So how can we tackle that problem? What we have been looking at is, can we essentially build a learning system, which we call a collective learning system, that's about 100 robots that are trying to learn all the skills from a standard tool set that you can buy in a tool shop. And these robots are now training and interacting and exchanging the knowledge that, based on this representation I was talking about. So the AI system kind of exchanges in this network of agents the performance and the way that they do different tasks. So each one of them is doing a different task. I won't go into details which ones they are. And then they raise their hand when they are done, essentially. And you can see, instead of weeks and months of training, these systems are able to sort or solve the entire usage of a toolbox that you can buy in any kind of standard commercial tool shop, and then use that system to then solve entirely abstract tasks that have not been trained and learned before. And what is most importantly is there is not a single GPU involved in that system. So this is all running on standard CPUs because of that the representation allows that you can actually do standard optimization algorithms instead of doing very, very intensive GPU calculation. So that system, the whole AI system runs about at, I think, 1 kilowatts for the 100 robots. That's the total energy that is required for that kind of AI. All right, so obviously one of the next questions you would be asking is, can we extend to the cyberspace? So can we actually now do these things in the physical world? Yeah, that's great, but it costs, it's very intensive, it's not scalable. So how can we make use of the physical simulating world, and can this be transferred to the physical real world? What you see here now is the key into a hole in a recent paper we published that is really about learning in the digital space how to insert, and the question, can this then be transferred into the physical world? We call this the sim to real transfer. So simulation to reality, a little bit like Neo when he was learning Kung Fu. So is the matrix really kind of close enough to the physical world so that the robot can learn in this digital space? And in one example we see here, we see a very abstract robot hand learning in the physical space how to open or how to turn the crank, we call that problem. And turning the crank is an example how to open a door, for example. And what you see here is now the same AI system running, not anymore just for robot arms, but now for hands, so very articulated systems. And what we can see now is that the system is training in various different scenarios in the digital world. And what we were able to achieve is, with this AI system now, a direct transfer to the physical world. So the system converges in the physical world, and with direct transfer is what you see now. The robot has never touched any door in its life, and immediately is able to grasp a door, open, or even adapt to this huge arrow you just saw that was about 7 centimeters, and is opening the door without having ever trained with a physical door. So now the next step is obviously, how do you feed that back into the digital simulation so that you can basically bootstrap and kickstart that kind of evolution between the cyber and physical embodied AI. So kind of the embodied AI scales now into the digital world and vice versa, which I think is kind of hopefully giving a bit food for thought, especially if you think about highly networked systems that could learn from each other and distribute knowledge almost like in network cascades. All right, so this is now even not only possible for very basic insertion problems, but we can now do single-shot transfer between various scenarios. And I think you have seen also various of the videos that are out in the wild at the moment of robots doing all kinds of things in the physical space, which I think gives also rise and hopefully some kudos to kind of what made that possible. So similar to the, let's say, GPUs in deep learning, we had finally a platform that was able to scale our global efforts in robotics learning, which was the Franka robot. That has been becoming kind of the state-of-the-art system for all kinds of machine learning approaches in the world. And this is the company that I founded many years ago. It's been out for many years as well. So, but nowadays it's kind of the standard approach and standard platform, especially for AI and ML research in the world. So if you see what publications are out there, they basically all are due to the open platform, the high data interfaces, and the kind of state-of-the-art system that now the world has access to. So I really think that this kind of combination of physical platforms that are open, that scale, but also that combine the right state-of-the-art have been really important to robotics, which kind of underlines that embodied AI cannot just be solved by pure digital aspects. So we actually need hardware platforms that do what we need. So we need our own GPUs, you could say. So, and as already said, what was really fantastic for us was in Germany to be recognized all, over the ocean. So I was kind of, it was interesting that even in 2024, there's a New York startup called Escape, and they use that robot now for massage robots. That was kind of interesting. And it again became a time invention of the year. So it's the same robot, but in a different clothing, you could say. All right, and what was actually really cool to see was that the entire world is now using these robots at all the big labs in the world to kind of really make robots learn to interact, to manipulate. So it's kind of an extension of what I could do in my own lab, but now actually the entire world is kind of, being part of that initiative and using these systems to create, I think, a fantastic kind of Wikipedia of skills, you could say, that then ultimately, hopefully, feeds back into the tree of robots that we're building, that then all robots could basically be kind of feeding into. So, but now I was talking about one robot embodiment. What about all the other robot embodiments? There's so many new ones. There's countless ones in the future. So what can we do with all the humanoids that are happening now? I mean, are we always needing 10, 20 years until new robots are there? So how can we systematize that process? It's really hard to build a robot. It costs a lot of money, and it's very hard to scale that thing. And now we even have robot rockets, right? I mean, what I'm seeing as a roboticist is basically a gigantic robot hand catching a rocket, right? I hope all of you see that as well. So basically, I see robotics problems all over the place. However, the quest for this fundamental embodied AI has kind of fundamental problems as well. In particular, the AI that we see today is very far from performance, let alone optimality. So often these kind of things we see there, they come from very, very deep understanding of dynamics, control, optimization. It's not straightforward to generate data. So we actually have a really fundamental problem in the data access to these systems. And then also there's the fundamental question, how can we systematically design a system that is able to do what we want it to do? Typically we build robots and then we see what they can do. So that's not a very structured approach. So we cannot really with algorithms, we can do so many things that these robots were never designed for, but can we foresee that? Can we actually now fundamentally build designs that do what we actually want them to do? So that the actual challenge number one is the data scarcity. As an interaction generates data and AI drives interaction, so it's a chicken and egg problem. We don't have the internet readily available. The robots have to generate the data to have skills, but they need skills to generate the data. So how can we solve that problem? And then second is the synthesis of the machines, which is fundamentally asking the question, can we build a robot compiler and a make engine that basically synthesizes automatically a machine based on specification? So, and I think it's really important to state that this is not a solution will not just come from fundamental model-based approaches, design or AI itself. I think it's really important that all of them work together. So fundamentally, the answer that I would propose is deeply rooted in physics and models, machine learning, and optimality. And how can we bring these fields together? So what we have been working on is what we call the optimal motion framework. So fundamentally, a system that is able to use very costly generated motions that typically come from optimal control frameworks, I'm going to talk about this in a second, and then encode them into AI systems so that even the AI then can generate optimal outputs. So optimal control in real time would be the optimal kind of AI, you could argue. And then the second one would be an embodiment compiler and maker. So basically from a phenomenology, so let's say I want the robot to throw a ball, to automatically synthesizing the robot that can throw a ball, and hopefully in an optimal manner. Okay, so let's go for the second one first. So let's say we want to develop a robot that is throwing a ball. Then you can obviously have multiple embodiments, so you don't see them visually the difference, but I hope you can see that this one is much more doing a typical human type of throw. The second one is more doing a swing up motion and then throwing the ball, but fundamentally doing the same thing. However, the morphology behind them is fundamentally different. So typically it would take you 10 years to build this robot, 10 years to build that robot, and then in the end you find out, oh, the second one is not doing what I want to do. So can we actually revert that process? So what we have been doing is really to use optimal control, and it's the only slide with equations. I just want to show you one thing. So what we really believe in is that the idea of physics, optimality, and machine learning have to be integrated. Why? Because we can formulate goals. So the cost function, that's the upper equation, is able to give us a notion of what is quality. The second one in an optimization framework is we can plug in the embodiment itself. So we now have an input for hypothetical embodiments that we could kind of come up with. We could use AI systems even to generate new embodiments, but the optimal control framework gives us the idea, this is where you can plug them in. All right, and then you can actually solve these problems, and depending on the embodiment, on the left one, you have a rigid robot, it does everything with brute force. On the right side, you see a much more gentle and much more elegant motion. That's actually a robot that has intrinsic elasticity, similar to humans, you know. The elastic elements in our body make it possible that we can store and release energy. Both do the same task, left one with very high power, the right one with more elegance, grace, and energy efficiency. And this obviously is only due to the very different mechanisms behind it. So that is great, but can we systematize that? I won't go into details, but what we have been recently proposing is basically a way to go from a purely observation to then propose dynamic phenomena that drive automatically cascaded kind of proposals of different mechanisms, templates, and anchors that ultimately can then be synthesized as a physical robot and that actually render exactly the let's say the phenomenon that you want to render. Yeah? Sounds almost like a specification. You tell the system almost like a search engine that can make robots. Hey, build me the robot that does X, Y, Z, and then the robot is compiling and synthesizing this. A student of mine is right now founding a company on things like that. All right, so what was the result? It's spectacular. Optimal embodiment, right? So this is a fantastic robot. It's able to, so we put all that knowledge into the robot, and the robot is actually not able to throw. Why? Because we asked it the wrong thing. Because there's another way to throw, which is much better. So the embodiment actually shows what it can do and what it cannot do. It's not just a brute force attack. So as you and me, we are built to do certain things. So one solution, this is the overhand throw. It's really bad at, but if you do the lower hand throw, it does a fantastic job, in fact. And why am I saying it's a fantastic job? Because if I compare it to the state of the art of all existing robots till today that have tried similar tasks, and you normalize them by numbers of degrees of freedom that you can use, and the size, obviously throw is depending on length, right? Then you can see that there is the standard rigid robots, and we have a new type of robot that really are using elastic and inertial energy transfer. So this is a huge jump in performance just by embodiment. So we can see a factor of 3 on the embodiment in performance of these systems. That really shows how much the body is important to be exploited and not just to be controlled away. And I think this is really a fundamental statement for embodied AI. So if we now go for the second quest, the optimal motion framework, so now we can synthesize the robot, but we need a lot of time to actually do the motions I just showed you. It typically takes 1 or 2 days to generate one of these motions. 1 or 2 days, just for one motion. So I want to throw a ball, let's say 6 meters. I need 2 days to compute that trajectory, throw it, and then I have to wait for another 6 days, depending on how accurate I want to model that. So how can we get that to a millisecond? And the answer is the following. I come back to the optimal control. This to be solved is quite an extensive problem, especially due to its high non-convexity, non-linearity, many constraints, and so on and so forth. But you can spend a lot of time of doing that, so you can generate offline data. So that's kind of the learning and optimization. So this needs a lot of time. And now the wishful thinking would be, can we encode that information into a beautiful machine learning system and then generalize such that it does it in real time at optimal performance? That would be the optimal AI you could generate, right? And we have been proposing a new method that basically uses a specific form of machine learning called dynamic movement primitives to then basically solve offline several optimization problems, then encode them into the dynamic movement primitives. It's essentially a latent space representation in dynamical systems, and then we are able to generalize in real time. And what you can then do is to compute the trajectory of a highly complex physical nonlinear system instead of hours or days, essentially in real time. So what you see here on the right side is now the bin is basically being moved, and instantaneously the robot is throwing into the bin. And we could show that the optimal manifold of the task space can be approximated with these machine learning algorithms absolutely accurately. So basically this means you could use optimal control theory to generate data that is optimal, to then learn how to optimally execute the right skills, which I think opens up a fully new perspective on how to really mix model-based algorithms with machine learning. Okay, so now for the last 2 or 3 minutes, I hopefully have, I want to now go to the second topic, which is much, much shorter, which I want to talk about is the AI for science part. So I've been talking a lot about embodied AI and how to build robots and so on. That's all beautiful, but what also is interesting and interests me maybe even more is how can we use these fundamental insights into acceleration of knowledge discovery itself. So basically that was the second Nobel Prize, right? The second Nobel Prize was given for groundbreaking contributions to protein science and kind of accelerated by AI. And I think it's quite important to state that this really shows what kind of magnificent tool AI is. So it has been used for prediction of proteins. It has been generalized to even more complex proteins. So there was, I think, 3 versions of AlphaFold. And it showed really the power that if you have the right data, if you do the right experiments, and you choose them very carefully, that the maximum insight can be generated, then you can use machine learning to really do the right prediction. So the generalization I showed you in the optimal control framework. So what happens if we now could use AI in a closed loop fashion to even accelerate the experiment generation process? Not only the aftermath, but actually the experiment itself. And that's where we need robots, right? Where we need embodied AI. If you don't have robots and embodied AI to fundamentally scale the knowledge discovery process, this will always be a decade-long effort of data generation, and then AI kind of kicks in. So how can we, really minimize the experimental part as well? And that's kind of what I call the AI accelerated discovery chain, where we kind of want to do experiment capabilities to automate. We want to have automatic state measurements, so every microscope has to become a robot essentially. And then obviously the learning and planning phase of the experiment to really have the full acceleration in the processes. So there has been lots of work on that in the recent 5-6 years on the automation of science, mostly lab automation, then some ideas of doing some next best guesses, GPs for experiment planning. However, I think it's still a major quest to fully automate these processes and really have a kind of a Jarvis, you could say, like the Jarvis of Iron Man. I would love to have one, probably in my lab. So can we actually do that? So let me give you an example of what I can see where robotics can really make a big difference. So let's say you want to interact with a cell as natural as it gets, right? Shaking hands with a cell. How can we do that? How can we use robotics AI to fundamentally make this an immersive process? Today, you would use an atomic force microscope. You tell it basically where to go. The force microscope goes there, here, and then pushes on via its cantilever on the cell, and then you can look at it. You can look at the data. That's about it, right? So it's more like a passive process. Next thing that people would now be doing is obviously, is to basically build a more complex cockpit, so you can do data augmentation and all kinds of things. But what I was thinking is, why don't we use telerobotics to these kind of cases? Maybe some of you have heard that in surgery we use robots to do minimally invasive surgery. In space robotics we use robots on the space station or even on Mars, interacting via telerobotics with the operator. We are using drones over kilometers. We can nowadays do surgery across continents. So why not using that idea to go down in scale, but in scale, not in distance. So, and this kind of idea is something we're building right now in the lab. So we're basically using a haptic input device that is connected to an atomic force microscope that is also connected to a multi-electrode, microelectrode array to then basically do an electrohaptic interaction and go in a feedback loop. So telepresence with individual cells. So you can stimulate the cell, you feel the cell, so you basically use robotic technology to interact now across scales in a closed loop fashion. And with this kind of idea, you can obviously now also robotize other devices such as a holomatography system, so a microscope, that now becomes essentially a drone. So it becomes, instead of just being a passive observer, the human looks into the microscope, then maybe you have a little bit of processing. We can actually automate the entire microscope to be an autonomous search and charge system. So what you see here is a fully autonomous workflow. The robot microscope basically is searching for the cells, building the 3D structures, and then automatically detecting the right cellular structures, and then being able to track them, to monitor them, so that you can then basically build them into a fully autonomous workflow. At the same time, Bayesian optimization has been really instrumental to do optimization from black box to even gray box systems. So you can now, again, I'm coming back to the physics modeling. So what we see now is that we can really accelerate the next best hypothesis planning via modern machine learning algorithms and really accelerate by fusing domain knowledge, such as certain constraints in assay optimization, for example, and other kind of processes that then can really accelerate the planning process and only do the experiments that promise the maximum output of what we want to have. And I think what this really gives us is a fundamentally new tool of knowledge discovery. Because what we have seen so far is, if you see the x-axis is the generality of things, the y-axis is the prediction effort, what we have seen and what the Nobel Prize has been given for is a prediction of a model with very, very high intensity of data, so a lot of data was generated, and it's still a rather narrow field. So I think the future really lies in fully automating the processes and really kind of use physics-informed machine learning methods together with the right experiment planning to really build kind of more and more a Pareto front in terms of the generality and prediction efforts that we can see. And I think what is really the promise that I think can really scale lab sciences and other experimental sciences is that the smarter the machines get, the faster we will actually see the right experiment to be done. And I think that really this idea of an AI accelerated discovery system, and we see here is a fully automated robotic laboratory we've been building that is doing all the standard lab works, and only with 2 students we can now run an entire laboratory in a fashion that I would say usually you would need 100 people to run that in manual work. So you can fundamentally scale science by embodied AI systems. You can use it for synthesis processes. You can do it for, charting and navigating through cellular systems. You can use it for the learning and planning. But I think most importantly, it is the first blueprint to actually think about how can we fundamentally automate knowledge discovery, if not even the scientific method itself. We see that many, many methods nowadays solve partial problems of the scientific method, right from the hypothesis generation to the selection, to the experiment planning I was talking about, the parameterization and then execution. But also in the evaluation and testing, I think we can see many, many contributions at the moment. And I think this brings me to the conclusion of today. So embodied AI is not only robotics, is not only the quest for universal intelligence, but I think it's even the automation of the scientific method itself that fundamentally can help us to crack the key to universal intelligence. Thank you very much.
All right, really fascinating. And I'm sure we have a lot of questions we want to expand and then to push the envelope to understand more. But let me just take the remaining 6 minutes to just extend a little bit on some dimension. So one of the last pieces you mentioned on this universal knowledge discovery is using the AI or embodied AI to assist human in this very intellectual process of knowledge discovery. So make me wonder, in this intellectual process, what is the best role a human can play in the scientific or in general universal knowledge discovery?
I mean, in a way, I think the human will always be the first one asking the right question. So there's the creative process of asking the question. I think I will always be the executioner, you could say. And also where, especially in the scientific discovery problem, the setting boundaries, setting intangible knowledge, parameterizing the AI to use domain knowledge will always remain the human scientist's responsibility. And at the same time, I think the human scientist might at some point become, he's spending more time on actually on the core science of things than to spend the time in the lab. Like I used lots of my time to build robots, to program them, to iterate. I feel that with these kind of tools, we're not writing binary code anymore. We will write, an analogy as a computer scientist, so we will not write anymore on machine level, but we will write on abstract kind of languages. And I think with this we can parallelize the scientific discovery process itself for us as scientists. Da Vinci died with a long to-do list, and I think we can reduce the to-do list a little bit if we can parallelize our scientific quest.
It's amazing, right? Yeah. And this, you can reduce the tool that we humans have to learn, but then you can focus on maybe higher level hypothesis formulation, right? Or maybe counterfactual reasoning to see if I don't do this, then what will be the outcome?
Yeah.
So you show a very interesting example that you work with your daughter on to test human capability of putting the key in the hole. So made me wonder that in this AI-assisted scientific process, we have a lot of students here in the audience also. I'm sure they all know how to put key in the hole.
I'm sure.
But then the question in this AI-assisted paradigm, what would be the skill and the knowledge set in the era of this embodied AI, no matter they are scientists or they are user, they are domain expert? What is the best way they can prepare themselves in this era of embodied AI, not only digital AI?
Right. I mean, it depends. It's a question that probably has not a single answer. I think it's really important to be either prepared to become a developer of embodied AI, or do you become a user of embodied AI, so a domain embodied AI expert. I feel that if you, for example, let's say healthcare workers or even medical doctors, I think they have so much to benefit from these technologies, and training them early on to be able to not only use the current state of the art, but also give their active input into what exactly the right technology is we should be developing, should be a core competency. Because it typically takes a long time to bring these two fields together until the right solution can be created. My experience has been that it takes often a year or two until you fundamentally speak the same language. And if you know, in the education of our young talents, we can prepare them to be early, not only adopters, but communicators and discussion partners that can really guide that process much faster, that would be a fantastic ability that I would have loved to have earlier on, to be honest. Yeah. That's the first one. And if you think about being a developer, I think it's really important to, first of all, the current AI doesn't solve the embodied AI problem. It's really very, very hard problems still ahead of us that require a lot of deep mathematical knowledge, lots of engineering knowledge, but also the bridge to the data science. So I think that's so really being open to that. What I see at the moment is a lot of dogmatism. I think it's really, the future will be more in integrating these approaches and be prepared to that. That's, I think, the two main take-home messages I can give.
So if we extend from that concept of integration or combine expertise, domain knowledge from different disciplines,
right.
As I mentioned at the introduction, Columbia AI unique concept is called AI plus X. So we are very proud that we're very active in advocating this cross-disciplinary collaboration across all different areas of AI. So what, in your view, what is the best way to conduct cross-disciplinary AI, particularly in the embodied physical AI space for university like Columbia?
I mean, to actually solve real problems that have meaning. I think one of the main problems, I mean, think about environment, think about sustainability or health. There's like real problems that AI can help solve. So if you think about, you have a wonderful colleague, Sunil Agarwal, a rehabilitation robotics expert in Columbia. He has his lab in the Columbia Hospital. So I think this is the way that these things can be done. This is unique. I don't think there is many places in the world where you can have this kind of intense handshake, and this is why so many of the things he has been developing translated into clinical reality. And I think this statement is probably true for many other, including financial sectors even. So I think this is the unique opportunity that I see here in Columbia, that it's one of the world's most prestigious universities, but also from technology to natural sciences, to social sciences, to financials, economics. I think there's all this unique pockets that can connect with each other and really, from the domain to the solution to really build systems. I truly think that many of my more fundamental insights typically came from solving real problems. Let me give you an example. Just today in the morning, while I was actually working on my talk, which I, by the way, never gave before, so I really tried to do a few things that I didn't talk about before. We were submitting two papers. One was a very theoretical paper about solving optimal control for nonlinear systems. Very hard to explain why this is important, but it solves a lot of problems for finance, for robotics, for neuromotor control, for many systems. But how did we come up with that solution? By asking the following question. in a rehabilitation scenario, you have a robot that is supposed to move your arm, and this robot is supposed to isolate the right muscle to do the right rehab motion. And from asking the question from the motion to the right muscle, we found out that there was no mathematical solution to that. And this led to 5 years of basic research. So one fundamental paper that was basically rehabilitation neuromotor control, and the other one really optimization and optimal control, applied mathematics basically. I think this is wonderful about our
Fantastic.
field. Yeah.
And it's really foundational theory can impact all different applications.
Exactly.
So you mentioned...
But the question was really not coming from the theory. That's my point.
I see.
It was I had no question on the theoretical side first, and I think this was I don't know. That has been my experience usually. Yeah.
It's really amazing you are able to abstract down to a common foundation,
Right.
optimal control or optimal embodiment, so that you can quickly in real time decide what is the best design.
Exactly.
So if I extend that question further, right, you mentioned rehabilitation, collaboration between science, engineering, and medicine. We at Columbia has so many sessions, as you see today, in finance, in creativity, in policy. So if I ask you to pick one area, in the next 5 years or 10 years, and AI is moving so fast here, what is the most exciting application through this cross-disciplinary application you will pick for the next 10 years?
For my own sake, I would probably pick the natural sciences, because I think the natural sciences at Columbia are quite amazing. So there's really leaders in many fields, and I see them I mean, I had brilliant discussions, for example, with Jim Hone. I always enjoyed this a lot. And he has also this idea of how can you use AI and robotics for his own material synthesis and finding new materials. I think this is intriguing. And I'm sorry to say that for all the other fields, which are probably equally interesting, but there's so many things you could be doing. I think there's a great focus here about health. Mental health is also one of the big focus areas I learned at Columbia. I think it's quite spectacular what could be done there. But in the end, what drives me at the moment is really this basic science question. Yeah, and I'm a bit of in my private life, I'm doing a lot of arts and music, so I would love to be engaged there.
Yeah, we have a session today about AI and arts and creativity also.
That sounds fantastic.
And Jim Hong, you mentioned, is a faculty member in the mechanical engineering, but he has really benefited a lot through the cross-disciplinary collaboration between engineering and natural science, in material science and quantum, in nano. So that's one of a very promising area that certainly embodied AI will be very useful.
Absolutely. And also with the Data Science Institute, I think you have a pretty amazing institution that really goes across many disciplines, and I think this is, I mean, also the neuroscience in Columbia is quite amazing to work with, I'm sure, and I mean, embodied AI and neuroscience also have very intense relation with each other. So I think we can probably continue for the next 2 hours too.
I do have 2 or 3 other questions, but the clock show had please close the program. And really wonderful, amazing presentation, no matter it's the tree of a robot, the safety, and also this optimal control design, and also the universal knowledge discovery, taking advantage of a cross-disciplinary strengths at Columbia. Really fits so perfectly aligned with our mission and vision. Thank you so much for your talk.
Thank you.
Thank you for joining us today.